So for this video, we'll give a mini lecture about angular momentum, and then talk about example problem number 3. So to begin, we'll just talk about angular momentum. It can be modeled or given by the equation L, angular momentum, equals angular velocity times moment of inertia. So for so as you can see, L, big uppercase L represents angular momentum, and then over here, as you can see, angular velocity is also equal to linear velocity over radius, and then moment of inertia equals mass times radius squared, or the integral of r squared dm. So we can use those for an example problem, but just to run over this quickly. So the moment of inertia, say we have an object with a mass equals 3 grams and kilograms, and radius of 3 meters. That's gonna mean I equals 3 times 3 squared. So that's just gonna be 27. The moment of inertia would be 27. So that just gives you a little example of how to do that. And for angular momentum, we're asked about that in example problem 3. The problem is a particle of mass of 2 kilograms is moving in the xy plane at a constant speed of 0.8 meters per second in the positive x direction along the line y equals 5 meters. As the particle travels from x equals -3 to x equals +3, the magnitude of its angular momentum with respect to the origin is blank. So we have to find the angular momentum. So first thing you always want to do for a problem like this is just draw a little model of what we're trying to find, so, and what the problem is explaining. So we're gonna draw -3 and then +3. So it moves from there to there, right? Along the line y equals 4 meters, so we can model this like this. This is at 4, 1, 2, so 4, this is 0. So as we can see here, it's saying with respect to the origin, what's its angular momentum, but as we can see, with respect to the origin, this is just going in a line, not like a circular movement around the origin. So there is no angular momentum in this situation, because if it were to be angular momentum, it would have to remain the same constant radius about the origin, which it says is what we're working about. So here, obviously, this is not this value radius from here to here is not the same as this radius of 4 right here. So for that reason, we can look at our answer choices. B 0 can't be B, C can't be C, C 4.8 can't be that. All of these it can't be, because it's not constant. For it to be constant, it needs to be moving around a circle. So just to clear that up, for problem 3, our answer is not constant because for a constant angular momentum, it needs to be a circle, and whereas in this problem it's not a circle, and without it being in a circle, it can't be constant.